Welcome, students, to my latest edition and installment on my never-ending lecture series on nuclear chemistry. In this lecture, I'm going to teach you about nuclear binding energy, about radiation, about nuclear power plants, and about what the fox says. Are you ready? Let's get started. In the 1930s, scientists discovered that the masses of nuclei are always less than the masses of their individual nucleons added up. For example, helium-4's nucleus has a mass of 4.00150 AMU. But its calculated mass, based on the added masses of 2 protons and 2 neutrons, should come to 4.03188 AMU. You'll notice that these numbers are actually a little bit different. The latter one is a little bit bigger. So why is helium-4's calculated mass 0.03038 AMU higher than its actual mass? The answer, as weird as this sounds, is that protons and neutrons actually weigh a little bit less when they're bound together in a nucleus than they do when they're individually separated. So at this point you might ask the question, why? Why? Well, when neutrons and protons are incorporated into nucleus, a certain amount of energy is expended to keep them together. This energy, called the nuclear binding energy, is obtained by converting some of those protons and neutrons' masses into energy according to Einstein's equation of E equals mc squared. The difference between the nucleus's calculated mass and its actual mass is called its mass defect. So once again, I hope you can wrap your heads around this. It costs energy to get neutrons and protons to be bound together tightly in a nucleus. That energy cost results in a change in mass according to E equals mc squared. And the change in mass ends up making it so that the total mass of those guys, when they're bound together, is a little bit less than what it would be if they were all separated out. Alright, so in the case of helium-4, we can calculate its nuclear binding energy from its mass defect like this. Delta E equals delta mc squared. Once again, c squared is a constant, speed of light squared. So we're really focusing on delta M. In the case of helium-4, I told you that the delta M, that is the mass defect, is equal to 0.03038 AMU. So you just throw this into the equation, and then you have to do some dimensional analysis gibberish to get it into SI units of kilograms. And hip-hop hooray, you have an answer that comes to negative 4.534 times 10 to the negative 12 joules. I realize that's a very small amount of energy, but it is the energy that a helium atom has to spend in order to get its protons and neutrons to bind together tightly in its nucleus. So in essence, this means that the amount of energy required to keep the neutrons and protons together in a helium-4 nucleus is 4.534 times 10 to the negative 12 joules. That also means that if you wanted to break apart a helium atom and separate out its individual neutrons and protons from each other, it would cost you that exact same amount of energy per helium-4 atom. Make sense? Good. Let's take a look at some problems. This first one says the mass of a proton is this number, and that of a neutron is this number. What is the binding energy in joules of a cobalt nucleus, keeping in mind that the cobalt nucleus's mass is this number? Now, I'm not going to do this for you here, but if you like, you can click the link here to a separate video in which I'll show you how to do it on the board. And now another problem. The mass of a proton is this number. The mass of a neutron is this number. The mass of the nucleus of an iron-56 atom is this number. What is the nuclear binding energy in joules for an iron-56 nucleus? Keeping in mind that the speed of light is this number right here. Now, I am not going to do this problem for you at all, but will invite you to attempt to do it on your own. Let's turn to another subject then, that of nuclear fission. Nuclear fission is the process of splitting heavier atoms into lighter ones, which gives off a huge amount of energy. This is the process used in nuclear power plants and in nuclear weapons. The first nuclear fission reaction discovered occurs when uranium-235 is struck with a slow-moving neutron, as shown in this figure. This causes it to split apart into krypton-91, barium-142, and 3 additional neutrons, as shown here. Now, heavy nuclei can be split in various different ways. For example, if I have one neutron collide with my uranium-235, it could split into tellurium-137 and zirconium-97 while giving off 2 neutrons, or conversely, it could split into barium-142 and krypton-91 while giving off 3 neutrons. Is there any way to control what it does? Unfortunately, not really. Now, just so you know, slow-moving neutrons are required to start these fission reactions. These neutrons are, of course, then absorbed by the heavy element's nucleus. Once that neutron is absorbed, the element becomes a highly unstable, heavy isotope that spontaneously breaks down or fissures into multiple lighter weight elements, as shown up here, which gives off a ton of energy. Now, you might notice that fission reactions also produce neutrons. We've got them over here. If these neutrons are slowed down in the presence of other fissionable reactants, then they can cause another fission, and then another, and another, and another, and so forth and so on. This process is called a chain reaction. The amount of fissionable reactant required to keep the rate of a chain reaction constant is called its critical mass. And just so you know, having an excess of fissionable reactant, or supercritical mass, can lead to a nuclear explosion. Parenthetically, I should mention that the critical mass of uranium-235 happens to be 50 kilograms per nuclear reactor. Speaking of which, here's a picture of a nuclear reactor. I won't go into detail describing it, other than to say that the heat produced by the fission products over here is used to boil water. The steam water then goes down a channel and hits a turbine, which uses the steam power to turn. That turns a crank fastened to an electric generator, which then produces electricity. In effect, then, nuclear power is very similar to most other means of producing electricity. It's just that the heat source comes from nuclear fission instead of fossil fuels, coal, or natural gas. To be honest, that's how electricity is produced, by turning a crank in an electric generator. That's really it. Most of the time, that's done by heating up water to steam and having it turn a turbine. There are, of course, conceptually other ways of being able to turn a crank in an electric generator. But if you're using water converted to steam, you have to have some sort of heat. Once again, that's usually done by exploiting the heat produced in nuclear fission in a nuclear reactor, or by burning fossil fuels, natural gas, or coal. But if you could come up with an alternative, cost-competitive, and efficient way of being able to boil water that doesn't have the negative aspects of these traditional means, I would love for you to do so. And I would also love for you to cut me in on the profit. Okay, now, as fission products accumulate inside a nuclear reactor, the reactor's efficiency decreases. So reactors have to be stopped periodically to replace or reprocess the nuclear reactants. Unsurprisingly, the fuel elements and rods removed are initially very radioactive. In the US, these are kept in storage at the reactor sites. In France, Russia, Japan, India, and the United Kingdom, these reactants are reprocessed. Storing nuclear waste is a problem, because it's radioactive and therefore very harmful to living things. It's estimated, in fact, that 20 half-lives are required for spent nuclear fuel's radioactivity to reach safe levels. Based on the 28.8-year half-life of strontium-90, for example, this would require 600 years to reach safe radioactivity levels. Polonium-239, in contrast, has a half-life of 24,000 years, so it's a highly undesirable byproduct. Polonium-239 can be reprocessed to ensure its breakdown into lower weight isotopes like strontium-90 that have shorter half-lives. With that in mind, I'm now going to show you an informative map. This informative map shows the number of operational nuclear power plants worldwide, as well as the number of currently under construction and the total percentage of each nation's power produced through nuclear fission. Of course, it's out of date because, this is a recording. But you're welcome to pause this video right now and take a closer look at it to see if you can glean anything that you find interesting. That takes us to the end of this video. Please stay tuned to the next video, in which I will teach you guys about the wonderful world of nuclear fusion. Until then, have an enjoyable rest of your day.